streaming, and last day we were. We didn't finish that? Finish that if you haven't already. But if you have, please take down these notes. I'll go back to that once I'm completely set up. Stop here, the third one. I would like you to draw the Bohr model of all three of these. Take the little notes that are on the side. And I'm just going to check who has finished. You can't see. Who sits behind you? Yeah. No one. I'm wondering if we should move you. Over there. Do you like it there? Because I'm going to be in your way a lot. If you would like to move, you're allowed. But if you like it there, stay. Oh, just on the other side of the classroom at an empty desk. Okay. Lucy, I don't have your Hebden yet. How far along are you? How far along are you? Okay, 1 second. And I'm also going to check. Okay, that one's good. Okay. Got that. We've got this. Get Class Dojo up and going. And attendance. That was the thing I had to wait to do. Sorry, I was still in your way. Brooklyn. Brooklyn's not here. Kaylee is here. Chet. Davis. And Denzi. I saw there. Dylan. There. Francois. Heather. Jaden is here. Jonah. Jonah, put away your laptop. Put in your bag. Simon. Why is your... What? Oh, aha! Oh, it's not that impressive, but there should be a sound of a heavenly chorus. You're welcome. No. It is similar, but contains less things. So if you have last year's and compare them, you'll go, oh, the things it doesn't contain is the things I have to remember now. Yeah. Oh. No what? Neutrons. Yeah. Hydrogen has no neutrons. Yeah. It's kind of weird. It's the only element you can taste. Sorry, protons are the only subatomic particle you can taste. Because it has no neutrons. Because if you take hydrogen, how many electrons does it have? 1. And if you take that electron away, it's H+. What's H+? H+ is acid. So if you, the sour taste of acid is you directly tasting, because you have little receptors to taste that, that's what you're tasting. You're directly tasting protons. So of the subatomic particles, the only one you can taste is protons, because everything else is all of them. Yeah. Yeah. Have you ever had anything with vinegar in it? Oh, vinegar's awesome. I love it. Pickles. I mean, pickles are great. Pickles are amazing. You take something that's basically trash, like a cucumber, and you put it in vinegar and wait a while, and then it tastes delicious. They're mostly water that tastes bad. Like, there's literally nothing of value in them. Yeah, so essentially they're a glorified sound effect. Yeah. But clearly you could attain the same effect from iceberg lettuce, which is also mostly water that doesn't taste of anything. So that's an improvement from something that tastes bad. Oh, no. I find it difficult to understand that some people choose to deliberately be wrong. That's always weird to me, but you're allowed to. As I say in Science and Ethics, one of the key components of attending my class, or indeed anybody's class, is you should not believe anything I say without checking it for yourself against a reliable source. There you go. That would be part of critical thinking. What counts as a reliable source? Google. Does Google have reliable sources? Yeah, so it can. It also has unreliable. So I personally choose Facebook. Yeah. Twitter is amazing because then they tell you really complicated things in really short amounts of words. Short words, good. Yeah. Sir. Yeah, obviously. No. Well, we agree. You were in my class last year. You know it's round. Round like a pizza pie! But we're not going to do that today. Of course it's not a sphere. Hold it. You were in Science Ethics. You tell them why it's not a sphere. What? Yes. What do you mean, where does all the water go? Why do you think it would leave? No. Hold it. No, because I can only take... Good point. Okay, because you said the water should be gone, which reveals an interesting understanding about things. Why do you think the water should be gone? Hold on. Is that how you think gravity works? Like no. In the sphere, under that model, wouldn't all the water just fall off the Earth? Yeah. Right. And so what do you think would happen on a plane? Would it? Depending on the depth? Because the gravitational pull sideways when you're on top of it is actually not that much, because a sphere, if you collapse it into a plane, they've done these calculations. So yeah, the gravitational pull anywhere would be much the same. You do get very interesting edge effects, because as soon as you try to go to the edge and you tip over, then you do feel all that pull. And what would that do? Pop you back up. So interestingly, in a planar model, the water wouldn't fall over the edge. Is this evidence that the world is flat? No, but it does expose that you may have been a little lied to by any teacher that suggested that water falling over the edge is a disproof. So you're undergoing now a little bit of cognitive dissonance, just to explain what's happening. And there is something called the backfire effect, where you'll reassert your prior belief, but stronger than before in the face of evidence. And so really, I'm just reinforcing your spherical model. You're welcome. Yeah. No, I don't. I do not. No, I did. Anyway, moving on. I've got Class Dojo here. Whoa. It is 9:06 p.m. Why is that's weird? What? Oh, yeah. That would be cool. Okay, actually, and oddly, since you just asked me a question, it's not me just picking on you. Francois was picked first. So, Francois, going back to this, what's this row? So, how many neutrons in lithium? Yeah. Its mass number is 7. Try it again. Protons are, yeah, 4. Nicely done, because we have that difference. Dylan, next row. (31) Number of protons. And number of electrons if it's -3. 18. Nicely done. Okay. And we're always changing the number of electrons up and down because we can never change that column. Because as soon as you change that column, you're doing nuclear chemistry where like you're literally changing what element it is. Anybody have any questions on that one? Excellent. So for these 3, so these ones here, we're only doing the neutral ones. What would it look like? Denzi, first one. I don't know why they're whispering. Why are you? No, Denzi. What would the Bohr model for hydrogen look like? 1 proton. No. No, you don't have to look it up. Because I told you how many it has here, see? 0 neutrons. Francois even asked a question on that. Hydrogen doesn't have any neutrons. Normally. I mean, there's isotopes of it that do. But this one doesn't. How many electrons would it have? 1. So we would go like that. And it's neutral. 1 to 1, so it's neutral. Veer. Veer left. Remind me to ask him questions as soon as he gets back. I already gave him the point. I don't want to undo it. Thomas. Helium. What's in the nucleus? Are you still doing it? Okay. Oh, hang on. And I'll help you through. How many people are still doing these? And I just went too fast. Just to make sure. No? Okay. So what's in the nucleus? You don't have to look at it any sheets of paper. It's literally like right here. Like look at the board. It's right here. Yeah. Sorry? You've added them. But how many protons are there? And how many neutrons? Excellent. Good man. I know when a teacher calls, it can be a little shocking. So we've got 2 protons. How many electrons are we going to have? What charge are protons? Protons are positive, electrons are negative, so we have 2, so we need 2 electrons. We go like this. Slightly more complicated. Simon. Lithium. What would the Bohr model look like? One second, yeah. And then, of course, we can keep going and going and going, but this illustrates the model. You fill up shells. You fill up shells closest to the nucleus first, and then when they're full, you move to the next one. How many are in the first shell? Then? No. And then? And then? No. 2 18s. So from the beginning, it is. Okay, we're not chanting well. Think Gregorian monks, all at the same time. 1, 2, 3, and the first shell there is.
2, 8, 8, 18, 18,
I heard it 36, but it's 32. Yes. And if you ever remember, the periodic table is not the electronic structure, but because the properties of the elements depend on their electronic structure, the very structure itself mimics the atom. So in the first row, we have 2. Second row, we have 8. Third row, 8. This row, if you count across, we have 18. We have 2, 10, and 6. Then we have 2, 10, and 6. And then remember this? It goes 56, 57, and then it pops down here to 58 and goes all the way across 71, and then back to 72 and all the way across. If you count all the way across that, it's 32. So you can always just count it off your periodic table. There's actually a deeper level here that we'll be doing too. These blocks matter. So in the first shell, there is 2. And the next shell, there is 8. But notice they're separated. It's not an 8, it's a 2, 6. And it goes 8, 2, 6, 2, 6, and then 2, 10, 6. And just to give you a little tiny preview, if we were to do an atom, it would have in the first shell, it has 2, and then 8. Oops, that's a bad 8. 2, 8, 8, 18, 18. That is what you've learned up until now. Very shortly, we'll be actually saying that this is 2, 2, 6, 2, 6, 2, 10, 6, and 2, 10, 6. Yeah, and remember before when I said, let's say we had an element that was 2, 10, I don't know, 1. So that would be gallium. Gallium forms +1 and +3 ions. And the reason it does that, let's get rid of that, is Control R to remove, is once that middle energy level is full, it drops down to here. And its number of valence electrons of gallium is only 3. Now remember last year, for those of you I had last year if you weren't here, but if I said, tell me the number of valence electrons in gallium, you would tell me 3. Because you'd go 1, 2, skip the middle, and then 3. It can form a +1 ion by getting rid of this electron, and then it can form a +3 by getting rid of these 2, and now it has +3, and its valence shell is empty. Those 10 actually just dropped away. And so that's quantum chemistry. They do that for reasons we'll go into a little bit later. I lie, really. We're just going to tell you it does that. Third year chemistry, they might explain why. When you do real quantum with like numbers and math. But really, this energy level is reflected in how they react. So even though this energy level is actually up there, because it fills up here, this is where we put it on the periodic table. So that's a little bit of what's coming. Now I'm going to ask someone, right off the spot, I'm going to say this is not neutral, but this is a +1 ion. How do we change that Bohr model? Heather. Yeah. Yeah. So when you take off electrons, you take them off from the outside. It's +1, so it has to have one less electron. We peel it away. So the things that we know, electrons are in a cloud. Now this is not looking like a cloud. If I have 3p, 4n, and I want to truly represent it as a cloud, I don't say that there's 2 electrons in here. I calculate the probability of where those electrons are, and the probability ends up looking like this for just a regular +1 atom. And if I can just, nope, that's not it. Y I literally used the exact same search term and it came up right away. Here it is. We've actually gotten good enough. And when I was in school, they did not have this, but they've managed to get so through some really clever techniques, get pictures of what atoms look like. So this is an excited hydrogen atom. You can see there's that first shell. It is in fact circular. It's spherical, unlike the planet. And here's the second one. This is an excited hydrogen. So the electrons aren't just here. They're jumping up and down because they've given it some energy. Probably in the process they have to do that. And so it's here in the second level. So this is the 8th level, and the hydrogen's spending some time there. And you notice the density is just less, the amount of electron we can find there. There's still only, if this is an excited hydrogen atom, there's probably only 1 electron, and it's spending some time here. And then it jumps and spends some time here. And you can calculate the probability of it being there. And with this picture, we can say, well, this matches our probability calculations. It spends very little time in here. And this whole jumping process is why we get the word quantum. Quantum, the meaning is really simple. It just means that you don't go from, it's like the difference between analog and digital. Analog, there's a continuous line from one thing to the other. In digital, it's either 0 or 1. Same with the quantum. You're either here or you're there. You're not literally running back and forth. Oh, because it's quantum. I once had a box of laundry soap that said worked with quantum power, which the only literal interpretation I could think of is that it was either clean or not clean, and it didn't go through any stages in between. And that's how electrons move in here. They jump from there to there because they're based on probability. They're not little billiard balls rolling around. They're waves that just appear in different spots. 2013. I think it was the first one. I have seen some bigger atoms, but the hydrogen is the simple one, so hold it. Let's go. Actual pictures. Okay. Why is Google like this? The first result that comes up is actual pictures of hemorrhoids. This is why I do this on the other screen. Because imagine if actual pictures of hemorrhoids just appeared on the screen. I'm not going to show you actual pictures. I just want to see for a friend. You can vote. Oh. Okay, so, whoops, wrong way. So when I type in actual pictures of molecules, and then I go. So we're looking at complex organic structures. You can see where the probabilities are in there. There's some larger molecules there. That's a very symmetrical one. That's pretty cool. This is made with atoms. So when they first started being able to take pictures of atoms, they started making pictures because, publish it in a magazine, look cool, get readers. And so when we say, how do we know it looks like that? How do you know this looks like that? We can say this is not just a prediction. We can actually do that. Now, the bigger it is, the easier it is to do. Which is why the hydrogen one is so cool, because that's the smallest. Oh, you bounce stuff off of it and see where it hits something. In the same way we take pictures of anything. When we take pictures with a camera, we're bouncing photons off things. When we take those pictures of bugs that are really close up, those are scanning electron microscopes. They bounce not light, but electrons. And then for this, I think they use electrons because they're taking pictures of electrons with electrons. So this is like taking a picture of a camera by throwing other cameras at it and seeing how they bounce. So you have to be really kind of good with the math and seeing how they deflect in order to get those pictures. Can you imagine trying to take pictures with it by throwing cameras and seeing where it sprays? And then you'd have to work backwards what the picture looks like. It would be kind of cool. Yeah. It's kind of how they do that. Now, are there any other cool pictures here? No, I'm not seeing it on my screen. And this is just really crossing my fingers that no pictures of hemorrhoids come up. But it's looking pretty good. It's all chemistry all the way down. I should. But actually, now that you say that, it's like, I should probably turn that on. But half the time, if I have it on, I don't get results I need. Which, hold it, that sounds bad. But, like, there's a ton of search terms, if you're doing, say, Biology 12, that get eliminated. And stuff gets flagged by Safe Search all the time that has nothing to do with anything. I think there's like a collection of little old men and women somewhere in the States that are just disliking things, and then they feed them into Google. And then they come up. Because it's not, Safe Search won't just take out, things like nudity. It'll take out controversial topics. Yeah. So when Safe Search is on and you're trying to search for something that just has to do with sexual reproduction, anything to do with sexual health, all of that just gets eliminated. So I frequently get irritated and then take it off when I'm trying to look for something just to make sure it's not being taken out by something else. But that's a really good point. Okay. We did that last day? Started it. Finish it. How many of you are done? Oh, no, you stop at calcium. How many of you are done up to calcium? Ooh. Enough. I'm going to give you like 5 minutes to finish it off. You can consult with the people around you, so if you're not done. And then I'm just going to start asking in like 5 minutes, maybe 4 now, what the electronic structure is going to be under each one. Boom, boom, boom. Now, was anybody not here last day and didn't get it? Ah. Do you have your Hebden here? Oh, okay. And do you need your periodic table to do this at all? No. If you're using your periodic table, you may get the number of neutrons wrong. Okay. Now you've freaked me out enough. I'm turning Safe Search back on. We are streaming. Hold it. Brooklyn Forester. Lillian Walter. That's someone I marked as here. Okay. So Lillian Walter, I forgot to mark as not here. You have about another minute. Come on, come on, come on. My schedule. And now it's not working that quickly. Okay, I'm going to go over this, but I'm not going to go over the entire Bohr model. I'm just going to go through the class. And where did that go? And ask just for the electronic structure that we're giving down here. And so we'll start with Valerie. What's the electronic structure of hydrogen? Oh, no, not the whole Bohr model. Just the electronic structure that you put down at the bottom. Yes, if it has any. One electron. That's it. So the electronic structure is just one. And then for helium, which I just noticed got kind of cut off. Sabrina? Yeah. Oh. Oh, how about for lithium? Yeah. And then Kaylee, what would helium be? Oh. Well, at some point I have to say we have to do it. Dylan. 2. Excellent. Kaylee, what would be beryllium? 2. And we'll just keep going. Start here at Simon. Keep going. 2, 4. Denzi. 2, 5. 2, 6. Come all the way back up to the front again. Francois. 2, 7. 2, 8. Gesundheit. 2, 8, 1. Veer. 2, 8, 2. 2, 8, 3. Yep. 2, 8, 4. Yep. 2, 8, 5. And then you can see the pattern. As, of course, it goes across, you're increasing the number of electrons by 1. And you'll notice then that the valence electrons for any family is exactly the same, which gives a huge hint as to why they would have the same properties. If your valence electrons are the same, you're going to react the same, and you're going to have many of the same properties. So now we can start answering some of these questions. Predict the electron loss or gain in each column. Veer, I'm going to start you off because you were actually gone when we asked the question. And I said, aha, we have to ask Veer as soon as he gets back. What would be the electronic loss or gain in this first family here? Why two, minus 2? Minus 1. Why minus 1? One of those. So we lose an electron. And what will that make the charge on this family? Positive 1. Excellent. Switching colors. And, oh, no. And Jonah, how many would the second column lose or gain? Lose 2 electron. And what would be the charge? Plus 2. Excellent. Let's do another color for here. That was good. Sabina? Pardon? It would be plus 3. Is that what you said? And would you lose or gain? Louder. Lose. Lose 3 electrons. Sabina, I have to apologize. I'm just realizing when I called your name before, I think I called you Sabrina. Chet. Next one. It can lose 4. What would the charge be then? Positive 4. Now, it's right in the middle. Why don't you say gain 4? It's Chet. What are you doing? It can be both. But are you saying that because you know or because you're just agreeing with Simon? Oh, well done. Excellent. Yeah. So it can be plus 4. It can also be minus 4. So carbon is plus or minus 4 depending if it loses or gains electrons. How do you know what it's going to do? Depends on what it's reacting with. So if carbon here is reacting with nitrogen, well, we know nitrogen. I'm going to ask that next. Oh, look, some nice teal. That's going to be Lucy. What is nitrogen going to do? Gain 3. And what charge would it become? Minus 3. So if this is reacting with nitrogen, which is minus 3, then it's going to become plus 4, and you get C3N4. And so in that case, it loses electrons. But if you take carbon and you react it with, say, magnesium, well, then carbon's going to gain electrons so that it can play with magnesium, which is plus 2. And so you get magnesium carbide. Carbon and silicon and germanium have twice the chance of a date on Saturday night because they, well, if you think of it that way, yeah, they can do anything they want. They are very open-minded. They are attracted to anything. They're willing to give electrons away. They're willing to take electrons. And that's one of the reasons why carbon chemistry is the chemistry of life, is carbon is very versatile. It's actually more versatile than silicon, but silicon has many of those properties, which is why it turns out to be really good for making computer chips with. It's more like a metal, so we can make circuits with it, but it can still do a lot of cool bonding stuff. So if you want hardware, you go to silicon. If you want wetware, you go to carbon. Wetware. Your brain is wetware. Yeah. Okay. Kaylee. This column, what is it going to do? Gain 2. And it's going to have a negative 2 charge. And Davis. Gain 1. Plus 1 charge? Minus 1. Excellent. Question? But there was laughter and I didn't get to hear the joke. What? Oh. Are you feeling personally proud? Well done. Well done. Jaden, what was the last column do? It'd be neutral. Why? Yeah, so is it going to lose or gain anything? No. Does nothing. This is why we call it the noble gases. Because nobility don't do anything. They just sit around their castles. If we put it in the modern terms, it'd be the 1% of the 1%. They just sit on piles of money, doing absolutely nothing. Bezos. So there's nothing in order for that to react. So we predict the electron range, we predicted the charge. Columns have the same loss or gain, which is why we call them families. So a little bit of review from last year. And this is also why we have something called the periodic law and why the periodic table is called the periodic table. Because if we go through, we get plus 1 ions, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1, 0, and then it's plus 1 again. And so they repeat. And when they repeat in order. And so it's a period because all the properties occur in a very periodic, very set basis. So grab those down. Then we have probably one more thing. The Hebden on the sheet is already updated in terms of tonight. What? No. Why? Write it down. Like I'm willing to wait, and writing it down creates memory. Yeah, and taking a picture just means it's on your phone. It doesn't mean you've done anything to put it in your head. Are you good, Simon? Okay. Oh, I thought you were still writing it down because you said picture. Anybody still writing? Oh, okay. Chet. Go, Chet. I'll put a little higher up so it's easier to see. Good? Okay. I have a very easy math problem that I want you to do in the most complicated way. Because we're going to do problems that you can't do the easy way. So the point of this is not to get the right answer. I know you know what the right answer is. Because if I have 50% of carbon 14 and 50% of carbon 12, what is the average mass of 14 and 12? It would be 13. You can do that in your head. It's really 14 plus 12 divided by 2. We're just seeing 13's the middle. We're going to do this in a way so we can do it when it's not 50%. Because the way of calculating average that math teaches you is when everything is equally weighted. And the probability we're going to use is when we have different amounts of each thing. So first we're going to take down this, and then we'll do the actual calculation. So getting this down. We have talked about the atomic mass being the average and the mass number being the same. In this one, we're going to calculate the atomic mass. We know our answer should be 13, but I'll show you the complicated way to do that. The little notation on the side for 50% is to remind you what a percent is. A percent is a way of representing a decimal for people that don't like decimals. So we say it's 50% instead of saying it's 0.5 because some people don't like 0.5. They're like, oh, that's complicated. But if you say percent, they go, oh, that makes sense. I honestly, that's really the only reason it exists. It's for accountants. So 50% is the same as saying 50 over 100 or 1 over 2 or any of those, or the same as saying 0.5. The percent sign just means the fraction times 100. Also, to define what an AMU is, or an atomic mass unit. Has anybody mentioned to you the time-traveling theory of electrons? If you do the math on an electron, and you go, what if the electron was traveling backwards in time? And this is true of all matter. Matter traveling backwards in time looks like antimatter. So if you have antimatter, it is functionally identical to regular matter that's traveling backwards in time. That doesn't mean that's what it is, but in terms of what the math works out to be with what we know about the universe, that's what it turns out to it could be. And one of the things that have puzzled is that protons are actually slightly different in different elements. The protons in a gold, although we pretend they're identical, are not the same as the protons in hydrogen. There's slight changes. But every electron is absolutely identical to every other electron. Absolutely identical. And so two physicists, one of them Heinemann, and I can't remember who the other physicist was, but two famous physicists were chatting, and they said, one of them was like, what if the reason all electrons are the same is because they actually are the same? It's all the same electron. There is only one electron in the universe. And what happens is that electron travels forward in time, and then when it reaches the end of the universe, it just travels back in time as a positron, antimatter electron that has a positive charge. And when it gets to the beginning of time, it turns around and travels forwards in time. And then when it gets to the end of time, it turns around. So every electron is the same electron traveling at different moments of its own time. All your electrons are, not your protons and neutrons, because they don't need this explanation. But every electron is. Now, there is a significant problem with this, which is, where are all the positrons? Because half the universe of electrons should then be positrons. There are some people who've come up with some clever explanations why it could still work. There's no experiment that we can think of that would prove it one way or the other. So it is at the moment just a thought experiment. Yes? I have seen Interstellar. Did they mention this in Interstellar? Oh, okay. Yeah. Yeah, because the time travel in Interstellar is very true. Like a planet that close to a black hole, how gravity affects time dropping down. And when you listen in Interstellar, you hear the music has a beat to it. They deliberately chose that beat because every beat is is a day passing on Earth. So when they're stepping forward and you hear like this, that's a day. And that's why when they go up, it's been, so long. Yeah. We should watch Interstellar. Yeah. Yeah. But, I mean, you have your access to your own time machines. As I mentioned the other day, I have a TARDIS. Doctor Who, TARDIS, it travels in both time and space. So, like, I get into this magic box, and when I get out, it's like 20 minutes later, and I'm at Costco. I traveled in time and space. I asked Kirk once if he was talking about time machines. I said I could show him one. So he was like, great. So I put him in the closet and didn't let him come out for 10 seconds. I'm like, look, it's 10 seconds later. You traveled in time. He actually thought that was really funny. Okay. Anybody still writing this down? Just the basic? No. All good? Okay. So, how we do this is we're first going to calculate if there's 50-50, I want to, if 50% of it is 14 and 50% is from carbon 12, what is the mass from that first 50%? If half of it's carbon 14, then what is the mass of that 50%? So it's 7. So I go 14 carbon is 14 AMU times, now we can't put percent down because we have to do that. So you can just go 50 over 100. Or if you can do percent in your head, you can just go 0.5 equals 7 AMU. And that is the mass from half of it. And then you go, well, now I'm going to do the 12 carbon. So I have 12 AMU times 50 over 100, which is 0.5. And I get 6 AMU. So half of it weighs 7 and half of it weighs 6. So the total mass, you add them together. Sorry, what? Jonah? Dylan? Isn't it? Yeah. Now, I am doing this in a very pedantic way. Like, you're like, this is very obvious. Couple of things. The units matter. You know that whole extending proficiency, all that thing you've been told? The communicating part, you sounded joyful. The communicating part, how do you communicate scientifically? One of the things I'm looking for with that is, do you have all your units? Because units in science matters. Units in math, they seem to like drop them all the time and they don't really care. But in math, it actually shows you what you're working with. We destroyed about, what was it, $15 million worth of equipment? Maybe more, I'd have to look it up, maybe less. But the US and the European Space Unit had a joint project where they sent a spacecraft to Mars, and instead of landing it gently as they were supposed to, it accelerated and smashed itself into the surface of the planet. Because one team was using force in pounds and one was using force in kilograms, and they forgot to communicate to each other what units they were using. So they got all the way to Mars and then smashed it to smithereens. They actually did that. Well, all the calculations to get there on the spacecraft, the units were all consistent. But the team responsible for the landing was using different units. It was a very sad day, I'm sure. That mission patch would be slightly tarnished. Yeah, I was on the mission where I was responsible for millions and millions of dollars. Although probably they blamed it on the intern. Yeah, the intern was supposed to say the units. You know, the unpaid person that gets all the... Their equivalent of the BFA. Yeah. I love the BFAs. We work them way too hard. Be nice to them. I would like you to do that calculation again, but with carbon 14 and carbon 12 with more realistic numbers. So now we're not doing 50%. This is probably a little bit more difficult to do in your head. And this is, you're going to get a much more accurate result. These are much more closer to the actual percentage, but you do it in exactly the same way. Sorry, I should have asked. Was anybody not done with this? Everybody got this down? Because this is what you're going to model it after. Anybody still writing? Davis? You were looking. Oh, you're doing that. Go then. Go. Next one. And I'm going to walk around. Oh. You know how I use Class Dojo, like to just like call in random people? You know what I found it can do? You know that whole new competency thing? I can program the competencies in, come in, take a picture of what you're doing, and just give you a competency. And it just records it. So I can record the observation and action. I'm astonished. And if I really want to, I can add your parents so they can see what you're doing on a day-by-day basis. And then every time you get points, they'd be like, look at my child. They're getting points. I mean, it's often used for elementary classes because they literally have to, look, Johnny walked today for the first time. Click. Okay, I want to see a result for this, the calculation. So, yeah, do exactly the same as the... When I walk by, if you have it done, point to the answer. Did you finish the previous one? Yeah, you did. Okay, but you're drawing it above it. The last slide? Does everybody have this one down? Is that what you need? Okay. Yes? Actually, I wonder if I could I set that up now? Francois. And then I can, how do I do that? Photo. Continue. Okay. And you just go like, where is it? Oh. And they go like, oh. Allow access to all photos. And then I can post it. And then theoretically, you can view your own posts. I don't think I'm going to take pictures of anybody else's because, where is it? Oh, there it is. Yeah, you're good. Hold it. What do you mean you don't know it's right? Are you confident you know how to do the math? Did you know what you're doing? Did you make a mistake that you can see? Then you say, I'm right. Excellent. Remember, if you're confident, you can become president. It actually doesn't even matter if you're right. If you're confident, there you go. I mean, something has gone horribly wrong. No, let me just take a look. Because you have 3 carbon 0.05. Oh. Do this one. I don't think it was. Oh, you've done it twice. That's what it is. It was 5%. 5% is 5 over 100. So you did it in your head and then did it again. That's all you did. You're missing some decimals. Much better. Include all the decimals for now. There you go. There. You're missing units. Okay, because to yours. Got units. There you got units. Good. I saw yours. No, something has gone on wrong here. 5 over 100 is 0.7. What's 0.95 times 12? You shouldn't get a number bigger. Yeah, so get 11.4, then add it up. How's yours? Something's gone wrong. Oh, no, you're adding it up. You're on the right track. How's yours? Oop. Yeah. So here, you've taken 5%, you made it 5 over 100, but then you just multiply it by 14. And then you times 12, yeah. And then you add those two together. Do that. Mr. Stick and say, I joined the town. Oh, go 5 divided by 100. Do you have a graphing calculator? Not a graphing. Do you have a scientific calculator? No, it's not. But then just multiply it by 14. Like you get a number, then go times 14. Show me that. Go to your back to your graph. And go times 14. Times 14. There you go. And yours was, where's yours? 5. Something's going wrong. Okay, so because you had one that was, it was 5% of carbon-14. So where's your 5% one? That one. So this is 5. So 5 over 100 times 14. That looked like an 11 to me, so I'm just rewriting it. Okay, that's right. And then 12 times 95, because it's 95%. Yeah. But do you see now? Yeah. So do that. You should get 12.1. Yeah. Yeah, I saw yours. Yours is good. Okay. You should get 12.1. But again, these are not the real numbers. This is actually something that really exists. It is present all the time. It's created in our upper atmosphere by cosmic rays. So cosmic rays come in from outer space, hit nitrogen, turn that nitrogen radioactively into carbon-14 that's unstable, and then undergoes nuclear decay. So this is being made and disappearing all the time. And it's not in the rock, it's in the atmosphere. So you breathe it in and incorporate it into your body. Plants put it in. This is how they can do carbon dating, because the amount in you is the same as long as you're eating stuff and you're alive. As soon as you die, all of that starts to go away. And that's how they do carbon dating. They just see how much is left, because they know how much you had to have started out with. But that's not the real amount. The real amount is that you have carbon-14. There's also a little tiny bit of carbon-13 and a little bit of carbon-12. Well, maybe a lot of carbon-12. And to be honest, these themselves are, I would have to include more decimals and a couple other isotopes if we were to get to the exact truth and how you get that number. But this number is close enough you can get really close to that number, because these are pretty much it. So do it with these numbers and then see what number you can get. Now, hold it. I can go around and take a picture and give you a competency. But I think if I give you access, you can take your own picture and supply it. Yeah, because you know what the definition would be, and then you're like, oh, look, I included all my units. Proficient. Oh, you have to do something extra. I wouldn't want to limit you. Yeah, so you have to go beyond. Maybe you looked up the real numbers and did it again. Yes? Did I not do this? Okay. We have, if you come to me and you say, what is my mark? We are all using a magic spreadsheet. And I use Excel spreadsheets. I know how to use them quite well. And if you ask me how it calculated your mark, the answer is honestly, I don't know. Because I put a mark in, and then a miracle happens, and then it spits a mark out, and I just put in competencies. However, no lie, I also am always really interested that how this is taught to us is definitely not taught in a competency-based model. But anyway, that aside, I also have taught chemistry, and I know what you need to do to get in Chemistry 12 in university. And we have been told explicitly that if the number that comes out of the competency doesn't seem right, I'm allowed to just give you what I think you're at. So in addition to using those words, I am also in Google Classroom, there are marks. And they're the marks I would normally give. And I will use those if that seems to make sense. So you don't have to worry that if the magic spreadsheet says that you can never do everything 100%. If you get 100% test, there's going to be a place that shows you get 100% test. The other thing I do is that if you use the competencies, the quiz is just a quiz. It goes through, it might be formative, it might not be. I put all that into Google, so I give you the grade you would normally get. And what I also normally do is that if you do better on the test than you did in the quizzes, so I add up all the quizzes together and get your average, if you do better on the test, they can replace quizzes because then they can just become formative because you showed me you learned, which seems to me be the real spirit of improving. So apparently the spreadsheet might automatically do that, weight certain things. You can make it weight certain things that are later more. But on the other hand, if you're really good at solubility, that shouldn't replace your mark on, say, stoichiometry. So there's problems with using it. I am going to have your new one and the one that has been trusted, and I'll just compare them and give you the one that you should have. Now, does that mean if you do better on the traditional one and the new one that I'll give you the traditional one? Yes. But it also means that if on the new one it says like you should have 95%, and I know you're not going to pass Chemistry 12 and you have no idea what's going on, but somehow mysteriously you've got a really high mark, then I'm not going to trust that either. And you and I have a conversation on why your mark is that way. Like it has to go both ways. Because my job is partially to give you feedback. No, that's all my job, to give you feedback, to see that's honest, that so you can know what you're going to be able to handle. That's it. So in other words, don't panic. I have done the worrying in advance for you. And if you're still worried about, come and see me, because the spreadsheet has tons of programming in it. And if you know how that works, I'll even show it to you. You can tell me how the mark is calculated. Yes? Oh, I count everything. The lab is almost marked. I was marking it last night. I'm almost done, so you should get those back soon. Who has not handed in the lab? No. Nope. What did I just say about quizzes and tests? Yes, but apparently you're not going to do that well in English, though. But yes. Sorry, I didn't mean to shut it down that much. Who has not done the lab? Okay. Actually, see me after, because I know you've had a lot on your plate as well. But everybody else has handed in. I am almost done marking it. What I do to make sure I mark everybody consistently, and I'm finally getting used to Google Classroom, it's taken me a couple of years. I used to mark them one at a time. Now I go through, I mark all of your, in the new ones, communication. So I name, title, date, APA format, I go mark everybody. And I try not to look at the name. I just flip through as fast as I can without looking at things and just mark them all consistency. Then I do all your procedures, then I do all your questions, then I do all your further questions, then I do your discussions, and then you do the conclusions. So I am hopefully putting as little bias as possible across all three classes. And I am done everything. I'm almost done everything up to the discussion. I just have the discussion and conclusions to do on the lab, and they should be done soon. I'm hoping to be done today. So hopefully today, if you get the marks back, it means I was. If you don't, then wait some more. But should be soon. Okay, when you're done this, you can go straight to the Hebden worksheet and start continuing on your Hebden. I'm going to come around to see what your answer was to this. That seems very off. Is it this one? 12 times 25, what is that number there? Okay, write that 12.1. First of all, I think you need to rate with a little bit more force. Okay, I don't think 12 times 95 over 100 is actually 12.1. Show me how you calculated that. Yeah. Cannot be. You can't get a mass, if you're doing the averages, you can't get a mass larger than the largest mass. So if it's over 14, you should get 12 point something. So there's something deeply wrong with that. You didn't take that and divide it by 100, I bet. There you go. One key point I just remembered, because someone, as we're using calculators, what kind of calculator do you need for this class? Scientific. Can that be a graphing calculator? No. And if you come with a graphing calculator, you will not be allowed to use it on a test. Scientific calculators are cheap. I mean, the school store is $15 or something. And that's not the cheapest I've seen. If you're really worried, ask your parents to send you one. You can find them on sale at Staples at times for like $8. They are not that expensive, but a graphing calculator can do too much and can actually be programmed to do things that would take away from our assessment of it. So in the same way that on the SAT and other things there's non-calculator sections, we don't use a graphing calculator. So make sure you get a scientific calculator ASAP. And then show adding those up. So you did have it. So show. So where would you? What would you show that? Yeah, and you're missing. Yeah, and every thing needs a unit. So everyone needs AMUs. Yeah, and so you're going to want to lay out your work just a little bit more neatly, space it out, make sure you're having your units in. Try this one. Okay. That is much better. Where's the rest? There's 15 questions to be done in there. You did one. Yeah, it asks you to do 15 of those. Yeah. Something's wrong with this one. Yep. It should come out near 12. So double check your results. Yeah, that should be right. Nope, there's something's wrong. .03%? Yeah, that might be it. Excellent. Include all the decimals, and you should get somewhere near 12.0103. Where? You in some way added up all the percents. So 0.0, that's 0.5 divided by 100, but you didn't multiply it by 14. Yeah. Yeah, you forgot to do that step. How's yours? Oh, okay. And how was yours? Oh, you're good. And I heard the cry of hurrah from you. Hurrah. Huzzah. Oh, excellent. Okay. Now, who else was I looking at? Did I see your calculation? Your calculation, that one? Did I see that? Oh, then that would do that. Yep. Perfect. Yep. No, something's gone wrong. Yeah, so it's not 0.5. It's well, okay. It's 0.5 over 100. 0.0. I don't know actually because you've got a number that's too big. So that's a 0.47. Yeah. Try that again. But is this the number? No, it's not. It's not. So check those again. Do them again. Oh, okay. Yeah, yeah. As long as you've got that, you're good. If you get 12.0103, you're good to do some Hebden. Oh, it's 1:14. Class is over in 50 seconds. So if you'd like to pack up at this point, I'm not going to say get out your Hebden for 45 seconds. But Hebden tonight is your homework. And if you and I could briefly chat. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Enjoy your afternoon. You're welcome. What? Yeah, it'll probably be. We're going to do our major test on that day. No, we're not going to do that. Really? You are missing a major test. Who's your bio teacher? Oh, good for him. Oh, that's probably why. He's way in Strathcona? Yeah. Okay. Yeah, catch up. Our major test will probably be after the break. Yeah. Once I know when it is, let you know. You're welcome. And